Verilog HDL. I am Dr. Suchitra, Associate Professor, Department of ECE, Vidyavartaka College of Engineering, Mysuru. Will be presenting on modeling and simulation of basic combinational circuit using Verilog HDL. As an example, full ladder is considered. The aim is to model in Verilog for a full ladder and add functionality to perform logical operations for the following gates: XOR, XNOR, and OR. Also, to write test bench with appropriate input patterns to verify the model behavior. This is the logic symbol of full adder. It is having three input bits A, B, C in and two output bits sum and carry. With three input bits, there are 8 combinations of inputs in the truth table, and these are the corresponding sum and carry outputs that are tabulated. This is the logic diagram of full adder realized using two half adders and a OR gate. The expression for sum is A XOR B XOR C in, and that of carry is A XOR B C in plus A in. Let us modify the expressions of sum and carry so that we can realize the logical operations of XOR, XNOR and OR gates. The expression of sum is A XOR B XOR C in. Considering A XOR B as one input X and C in as another input Y, X XOR Y can be written as XY bar plus X bar Y, replacing X with A XOR B and Y with C in. We get the modified expression of sum as A XOR B C in bar plus A XOR B whole bar C in. Let us consider this logical expression as equation number 1. The carry expression is A XOR B C in plus AB. ANDing the second term AB with 1, that is C in plus C in bar, and expanding A XOR B as A bar B plus AB bar in the next step. Let us remove the brackets. We get the following terms of logical expressions. Taking C in common in these two terms, it gets reduced as AC in, and once again taking C in common from the first two terms, we get the expression as C in into A bar B plus A, which is nothing but C in into A plus B. So this is the final modified expression of carry. Let us consider this expression as equation number 2. We'll consider only equation number 1 and equation number 2. Suppose if C in is equal to 0, in equation 1, the sum will be equal to A XOR B. That is, with C in equals 0, the output at the sum will be same as that of the XOR gate. And with C in equals 0 in the modified expression of carry, the carry will be equal to AB. That is, the carry output will be same as that of the AND gate. Next, with C in is equal to 1 in the expression 1, the sum output will be same as that of XNOR gate, that is A XOR B whole bar, and the carry output will be same as that of A plus B, that is the OR gate. This is the truth table of full adder. We can observe out of the 8 combinations, there are 4 combinations with C in equals 0 and the inputs A and B acting as 2-bit inputs with the combination 0, 0, 0, 1, 1, 0, 1, 1. With this set of combinations given as input to the full adder, at the sum output we can realize XOR operation, and at the carry output we can realize AND operations. The remaining 4 combinations are with C in is equal to 1 and AB again acting as 2-bit inputs 0, 0, 0, 1, 1, 0, 1, 1. With this 4 combination of inputs given to the full adder, At the sum output, we can realize XNOR operation, and at the carry output, we can realize OR gate operation. This is the Verilog code of full adder. Starts with the keyword module, name given as full adder, the port list, A, B, C in are the inputs, sum carry are the outputs. Temp is the variable declared as reg, 2-bit variable initialized as 00. Always add sensitivity list A, B, C in whenever any of the input changes. Temp will be equal to A plus B plus C in. Before the module is ended, the LSB bit of the temp is assigned to sum output and the MSB bit of temp is assigned to carry output. Once the code is entered, we need to simulate it in order to test whether the design is correct. A test bench provides a stimulus that drives the simulation and checks the response. So test bench is again a HDL module used to test another module under test. It contains input and output patterns called as test vectors. It includes keywords such as initial, begin, end, hash delay to provide delay between the input vectors. Time scale sets the time unit. So this is the test bench of full adder named as FA. The inputs declared as REG, TA, TB, TCin, and outputs declared as wire, tsum, tcarry. The module under test, that is full adder, is initiated here. Positional mapping, TA, TB, TCin in the order of inputs, tsum, tcarry in the order of outputs. As discussed before, the 8 combinations of full adder separated as 4 combinations with TCin equals 0 and 4 combinations with TCin is equal to 1. The design is simulated using Xilinx ISE tool. Integrated Software Environment is a tool provided by Xilinx to configure FPGA. ISE is an integrated collection of tools accessible to GUI. Next, let us enter the design and simulate the tool. Let us first invoke the tool. This is the source window. This is the process window. The first step is to create a new project. We'll go to the option File, New Project. Enter the name for the new project. Check the specifications. The FPGA family is Spartan 3. The device is XC3S50. Finish creating the new project. The next step will be to enter the design file of full adder. For this, we'll go to the option Project, New Source. Enter the name for it. It's a Verilog module. We can either enter the inputs here or we can directly enter the design in the file. Save the file. The next step is to add the test bench file. For that, we'll go to the option Project, New Source, Verilog Test Fixture, name for it. Then let us enter the test bench code here. Save the test bench file. At the drop down in the source window, change the option from synthesis to simulation. So within the project, we have two Verilog files. One is the design file and the other one is the test bench file. Let us first check for syntax, and then let us simulate the behavioral model. This is the simulation waveform of full adder. For the first four combination, T C in is 0. A B inputs are 0 0, 0 1, 1 0, 1 1. Sum output is same as that of XOR gate, and carry output is same as that of AND gate. The next four combinations, C in is equal to 1. A B inputs are 0 0, 0 1, 1 0, 1 1. The sum output is same as that of XNOR gate, and the carry output is same as that of OR gate. Thank you.
Hello everyone, welcome to the faculty.
We just saw the implementation of the full ladder. So don't worry about the test benches. So we need not require to write the test benches as we already know. So learn the coding, okay? Understand the logic design and learn to code with the proper syntax. So next I'll be explaining you one more program with the help of the same videos. So these videos are very helpful, guys. So just I've shared the link also. Just go through it. Okay. First, next program is about your ALU. ALU perform the arithmetic and logic operations. So we are trying to design a 32-bit ALU. So it has to perform the following things. Let us see how the coding is done here.
Various tasks for a 32-bit input. This table gives a brief description of what all the operations we can do with a 32-bit ALU. Okay. I have to use an opcode which is purely a 3-bit vector quantity. The opcode can be 0002 111. Based on each opcode selection, I have to perform a required ALU operation, A plus B, A minus B, increment operation, decrement operation, complement, logical OR operation, and logical AND operation. Okay, I can perform this operation based on the control signal. Means only when enable is high, the required opcode can be selected, and based on the opcode selection, the arithmetic and logical operation can be performed. Suppose if enable is made 0, the output of each condition should go to high impedance state, irrespective of any opcode selection. And along with that, I am using one more signal called acknowledgement signal. This acknowledgement signal will be high only when the operation is successfully completed. If each operation is not successfully completed, the acknowledgement signal will be always active low. Okay, this is the system diagram I'm using for my 32-bit ALU, where A and B are purely 32-bit input quantity, and opcode is a 3-bit vector, enable is a scalar variable, and result is 32-bit vector. Let's see how we can do this with the help of Verilog code. As we already know that every module should have a keyword module, and correspondingly we should use end module keyword. Okay, the syntax for writing the module description is that we have to use module followed by module name. Here my module name is ALU, followed by we have to give what are the input and output system specification we are using as a terminal list. Here A, B, E opcode are the input port. Therefore, I am declaring these variables as a terminal list. Similarly, y, ack are my output signal. Therefore, I have to declare these two signal as a output. You can observe that A and B are my 32-bit input. Therefore, I have to represent it as an input port with a 32-bit vector 31:0. Similarly, based on enable signal, I have to perform arithmetic and logical operation. Since enable is a scalar quantity, you have to declare it as an input port. And again, irrespective of 32-bit input, I had to perform logical AND operation or operation and arithmetic operation based on opcode. You have to declare this opcode as an input port with a vector of 3 down to 0. Finally, for each opcode selection for 32-bit input, I am getting the result of 32-bit itself. Therefore, variable y I am declaring it as an output with a vector of 31:0. And as I already specified in the earlier slide, after each successful operation, the acknowledgement signal should go high. Therefore, ACK, I am treating it as an output signal. Since we are writing the code in behavioral description style, all the output variables, irrespective of whether it is scalar or vector, we have to store it in a register. Therefore, I am storing the same using RED data type. Okay, once input ports and output ports are declared, I am writing the sensitivity list always at A, B, E, opcode. Means these are my concurrent input to my process. Okay, after that I am using a begin keyword, and again here I am testing. If enable is 0, irrespective of any opcode, the output should result in a high impedance with a vector.
64 guys. Why this value 64? It is taken as 64 because we are trying, if you try to add 2 bits, 32 bits, so the size should be double. Okay, 32 32 is 64. That's why the output is given as y is equal to 64 tick high impedance. Okay, so if you add the two numbers or if you multiply, the multiplication is not possible. 2 32 bits, if you multiply again, the value will be more. So that's why you have the y output as 64 tick dz. Okay,
Vector of 64 bits. The main reason behind selection of 64-bit is that even if I choose a variable a and b as a 32-bit quantity and perform multiplication operation, the word size may be double.
more.
Due to that reason, I
Hmm.
am increasing the word size to 64. Okay, y is always 64-bit high impedance if enable is 0. And again I am writing the condition else. I am making the acknowledgement signal as high because I have not performed any arithmetic and logical operation till now. Okay, now after these conditions, I am writing the case statement. I am processing the opcode. If opcode is 0, I am performing addition operation. If opcode is 1, subtraction. Opcode is 2, negation. Opcode is 3, a plus 1. Similarly, if opcode is 7, I am performing logical AND operation. Okay? And I am ending the case. And after ending the case, I am writing the acknowledgement signal as 1. Means after each successful arithmetic and logical operations in the case statement, this acknowledgement signal will remain in an active high state. And after this, I am ending the if statement and I am ending the sensitivity list, and finally I am ending the module. Let's see how we can do this with the help of Xilinx. Open the Xilinx tool. Go to File menu, select New Project. In the new project, I am storing all my files in the C drive Xilinx folder. I am giving the project name as ALU and selecting the top level source type as HDL. Press next. Since the project is already exist, I am giving different file name ALU12. the next button, you have to select the device here. I'm selecting the device as Spartan 3. Family name Spartan 3, device name XC3S50, PQ208-5. Okay. And after this, I'm pressing the next button. Press next again, and finish. Okay. Now make sure that the device name along with the speed and the total number of pins are properly displayed once you create the project successfully. Now we have to open the editor window to write our Verilog code. I will select a blank text file. Since I developed the code already, I will paste here. I will save this file name alu.v. Okay. After this, right click on the device, click on add source, select your code, press open button, press OK. Okay. Once you have completed with this procedure, the next step is to check for any errors in the program. I'm checking for syntax errors. Select your program. Under synthesize SXT, double click on check syntax. Check syntax is being checked now. It is running. You have to wait for a few seconds to get the process completed. Okay. You might have observed that the program contains an I modified this syntax error, and again I am rerunning for the check syntax. Now the check syntax process successfully completed. Means that I don't have any error in my program. And now I want to check what would be the result for my each input A and B based on the enable and the opcode selection. We have to write a test bench for this. To write a test bench, right click on the program, click new source. Select Verilog text picture, give file name as ALU, giving file name as ALU test, next, binding with my module, finish. To perform this operation, okay, the Xilinx itself will generate the module along with that list of variables as an input as well as a output parameter. You can observe that the module consists of a test fixture name ALU test underscore V, but it does not have any terminal list. Okay, this text picture we also call it as a stimulus block. Okay, you can refer the details of stimulus block in the Verilog HDL by Samir Palnitkar textbook. And whatever the variable that I choose as an input will be considered as a register, and the output variables will be treated as a wire. Okay, once all the registers and wires are declared in the stimulus block, we have to instantiate the design using hierarchical name reference concept. Again, you need not to create any instantiation here. It is done automatically by the Xilinx compiler itself. Okay, after that, irrespective of my any input, the initial value of my A, B, E and opcode is considered as 0. Again, this is the default value given by the Xilinx compiler itself. And after giving the initial value, Xilinx itself will generate a global time of 100 nanoseconds. Okay, only after this only we have to paste our input combination. We do this. Back to the slide. So, since I already explained that module does not have any terminal list, I am choosing it as a TF in my test bench waveform, and all the registers are treated as an input and all the outputs are treated as a wire. And here the design is also instantiated within the stimulus block. And initial value, as I already explained in the Xilinx compiler will generate the initial value of my inputs as 0. And now we have to give a combination of input. Okay, I'm copying all the possible input combination Then I will paste in the silver scroll. After this, press save. To observe the result, change the sources from synthesis implementation to behavioral simulation. Select your test bench waveform, simulate behavioral model. Double click on the simulate behavioral model. Click on the, there are some errors. Line number 58. Here I wrote it as a semicolon. Again, save, select your file, double click. Once you double click on the simulate behavioral model and check the output. If enable is 0, we'll choose the marker. We'll choose enable 0, output is Y. I'm giving input as 8, 8 plus 16, 8 plus 6 is 14. Okay, 8 minus 6 is 2. 8 plus 1 is 9. Here you can observe that the table 8 plus 1 is 9. 8 minus 1 is 7. Again, A is displayed. Complement of A. Here, A and A or of B result. Here you can observe A and of B result. Okay. If you want to observe hexadecimal equivalent of this, it is available, and acknowledgement signal is high for all successful arithmetic operation. Okay, that's all about the ALU experiment. Thank you.
Okay, this is what is the ALU implementation. So these programs, these 4 programs, you have to practice in the lab. So many of you are opted for contact class, that is contact labs. So once you come to the lab, so you should be ready with this program. So we'll start programming as soon as you come to the lab. So with this, I'm ending today's class. If you have any doubts, you can ask me. Otherwise, mark your attendance. All the videos are shared in the Google Classroom. Just go through these videos.